What if I told you that everything in the universe, every star, every planet, every molecule, and even you, began from something smaller than an atom? It's almost impossible to imagine, right? But that's the story of the Big Bang, a moment that changed everything. This wasn't an explosion in the way we think of it. It wasn't a fiery blast ripping through space. Instead, it was space itself, stretching, growing, unfolding in all directions. It's a story of beginnings, of time, space, matter, and energy. But what happened during those first moments? How did the universe grow so rapidly from something so small? And what does that mean for the universe we see around us today? In this video, we'll journey back to that extraordinary moment, the birth of the cosmos, and unravel the mysteries of the Big Bang and the incredible expansion period that followed. Let's rewind the clock back 13.8 billion years to a moment when everything we know and see today didn't exist. No galaxies, no stars, no atoms, not even space or time as we understand them. Instead, there was a single, unimaginably small and dense point, known as a singularity. This singularity contained all the energy and matter that would eventually make up the universe. But here's the catch. The Big Bang wasn't an explosion. It wasn't some kind of fireball blasting through empty space. Instead, it was the rapid expansion of space itself, an event that marked the very beginning of space-time. Think of it like this. Imagine a balloon with tiny dots on its surface. As you blow it up, the surface expands, and the dots move further apart. Similarly, during the Big Bang, space stretched in every direction, carrying everything with it. But this was no ordinary expansion. It happened incredibly fast. In the first fraction of a second, trillionths of a second. In fact, the universe expanded from something smaller than an atom to larger than a galaxy. This period is known as cosmic inflation. The conditions were extreme, beyond anything we can truly comprehend. The universe was incredibly hot and dense, with temperatures exceeding 1,000,000,000 degrees. This heat was so intense that atoms couldn't form. Instead, the universe was filled with a seething soup of elementary particles, quarks, gluons, and photons. Quarks are the tiny building blocks of protons and neutrons, while gluons act like glue, binding these quarks together. Photons, the particles of light, were also present, but couldn't travel freely because they were constantly interacting with the other particles. It was in this chaotic environment that the first particles started to form. Quarks began to combine, giving rise to protons and neutrons, the basic components of atoms. But full atoms wouldn't exist for hundreds of thousands of years. For now, the universe remained in an incredibly dense and hot plasma, expanding and cooling as it grew. This early period set the stage for everything to come. The universe wasn't just expanding, it was also cooling down. And this cooling was crucial because it allowed for the formation of more complex structures, leading eventually to the stars, galaxies, and life we see today. But what drove this expansion? And why did the universe grow so rapidly? To answer these questions, we need to understand the forces and energy at play during this remarkable event. After the Big Bang, something extraordinary happened, an event we call cosmic inflation. For a fraction of a second, the universe expanded faster than the speed of light. In that tiny moment, it grew exponentially, from smaller than an atom to something many light years across. This might sound impossible, since nothing can travel faster than light, right? But here's the key. It wasn't things moving faster than light. It was space itself expanding at a mind-boggling rate. Why was this inflation so important? It did two critical things. First, it smoothed out the universe. Before inflation, the early universe was chaotic and dense. But as space expanded so rapidly, any irregularities were stretched out, making the universe remarkably uniform. Second, inflation created tiny quantum fluctuations, random variations in energy on a microscopic scale. These fluctuations were stretched out as well, and they became the seeds for everything we see today: galaxies, stars, and clusters of galaxies. These tiny differences in density determined where matter would clump together in the future. As inflation ended, the universe continued to expand, but at a much smaller rate. And as it grew, it began to cool down. In the first few minutes, temperatures dropped enough for the formation of simple atomic nuclei like hydrogen and helium. But it was still far too hot for full atoms to form. For nearly 380,000 years, the universe was filled with a hot plasma, a chaotic sea of charged particles, including protons, electrons, and photons. Photons, or light particles, were constantly colliding with the charged particles, making the universe opaque. But then came a pivotal moment, called the recombination era. As the universe cooled to about 3000 degrees Kelvin, electrons began to combine with protons, forming neutral hydrogen atoms. For the first time, light was able to travel freely through space. This first light is what we see today as the cosmic microwave background, or CMB. It's the oldest light in the universe, a faint glow left over from those early times. By studying the CMB, we've created a snapshot of the universe as it was just 380,000 years after the Big Bang. Those slight variations in temperature and density you see on the CMB map, they are fingerprints of those quantum fluctuations from inflation, now imprinted on the universe at a massive scale. Over billions of years, those tiny variations grew under the influence of gravity, forming the cosmic web of galaxies, stars, and clusters we see today. Without cosmic inflation and the seeds it planted, the universe as we know it would never have taken shape. The expansion period wasn't just about the universe getting bigger. It set the stage for everything: the formation of structure, the distribution of matter, and even the conditions for life. From this chaotic, high-energy beginning, the universe began its journey to the vast, complex cosmos we observe today. The Big Bang Theory isn't just a fascinating idea, it's one of the most well-supported scientific theories we have about the origins of the universe. Over the decades, astronomers and physicists have uncovered multiple lines of evidence that confirm this remarkable event. Let's explore the key piece of evidence. First, there's the cosmic microwave background, or CMB. This faint glow of light is the afterglow of the Big Bang, released when the universe became transparent, about 380,000 years after it began. Scientists discovered this radiation in the 1960s, and it matched precisely what we'd expect if the universe started from a hot, dense state and expanded. These tiny variations in the CMB reveal the seed of galaxies and clusters we see today. It's like a baby picture of the universe, and it's one of the strongest confirmations of the Big Bang. Another key piece of evidence is the abundance of light elements. especially hydrogen and helium. During the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur, creating these light elements in specific proportions. Today, we observe that about 75% of the universe's normal matter is hydrogen and about 25% is helium, with traces of lithium. These ratios perfectly match predictions from the Big Bang nucleosynthesis model. If the universe had a different origin, we wouldn't see these specific abundances. The third major piece of evidence comes from galaxy redshifts. When we observe distant galaxies, we see that their light is shifted toward the red end of the spectrum. This redshift occurs because space itself is expanding, stretching the light waves as they travel towards us. Edwin Hubble discovered this in the 1920s, and it revealed something profound. Galaxies are moving away from us, and the further away a galaxy is, the faster it's moving. Exactly what we'd expect in a universe that began with a Big Bang and has been expanding ever since. And here's the incredible part. The universe hasn't stopped expanding. In fact, it's speeding up. This acceleration is driven by a mysterious force we call dark energy. While we don't yet fully understand dark energy, we know it makes up about 68% of the universe and is causing galaxies to move away from each other faster than ever before. These discoveries not only confirm the Big Bang, but also shape our understanding of the universe's future. If the expansion continues to accelerate, the universe could end in a big freeze, where galaxies drift so far apart that stars run out of fuel, and the cosmos becomes cold and dark. But for now, studying this expansion helps us uncover more about dark energy, the ultimate fate of the universe, and the origins of the very structures we see in the cosmos today. The evidence for the Big Bang isn't just written in the distant past, it's all around us. Every time we look at the CMB, study the elements, or observe galaxies moving apart, we're seeing the echoes of this extraordinary event. It's a reminder of how science helps us explore the most profound questions about where we come from and where we're going. As we look back 13.8 billion years ago to the moment of the Big Bang, we are reminded of just how far the universe has come, from a tiny dense point to the vast, awe-inspiring cosmos we see today. But what about the future? Will the universe keep expanding forever, growing colder and darker as galaxies drift apart? Or could something unknown, perhaps dark energy, reshape its destiny? These are questions we've yet to answer, and they are among the greatest mysteries of science. Every new discovery brings us closer to understanding not just how the universe began, but how it will evolve and eventually how it might end. So, next time you look up at the stars, remember, they are not just lights in the sky, they are pieces of a puzzle that spans billions of years. And who knows, the next big discovery might just change everything we think we know about the cosmos. What do you think the future holds for the universe? Leave your thoughts in the comments and let's keep exploring the greatest story ever told together.